Hey, hello everyone. This is Ravishek Dixit from VibroSystM Canada. I am the business manager. Business manager. Canada. I am the business manager for Nepal, Bhutan, and Sri Lanka. It is my privilege to have my colleague, Mr. André Tétreault, Director Test and Diagnostic at VibroSystM Canada. He is the member of several reputed international organizations like SIGRE, IEEE, and EPRE. And today he will start demonstrating some of case studies from hydro and turbo as well. Before handing over this floor to Andre, I would like to share my experience, which I observed in India with our unique solution, Zoom Zero Outage Online Monitoring at THGC's small hydropower plant at Dukwan. I was commissioning the vibration monitoring system with Zoom software at Dukwan, and I observed high vibration, high relative vibration in TZB. So I discussed it with my diagnostic team, with my engineering team, and after that we found they were real, and customer refused that they were not real. So we said they are, and afterwards we suggested customer to open their guide bearing pads, and afterwards they opened their guide pads, and they found their irregular guide bearing clearance. They reset the bearing clearance, and afterwards the vibration values were within range. So it was the experience which I observed in India. So there are several cases where we observe such issues. We diagnose such problems in entire world, and we saved thousands hydro and turbo units from being minor or major damage. We avoided several unplanned outages. So now I'll request to my colleague, Mr. Andre, to demonstrate some of case study. Then we will take the question and we'll try to reply of all the questions.
Okay, thank you, Ravishek. Good afternoon, everybody. Thank you all for joining us today. As mentioned, my name is André Tétreault, and I am the Director of the Test and Diagnostics Department here at VibroSystM. Just a basic background from my perspective. I've been working for VibroSystM for over 25 years. In the past 15 to 20 years, have been involved in the diagnostics of large electric rotating machines in the turbo industry, both fossil fuel and nuclear, working on the hydro side as well. Plus we work also on large SAG mills and ball mills in the mining industry. So we have a lot of experience in the behavior analysis of large rotating electrical machines. What I want to discuss today, this is just a brief glimpse at what we do on a daily basis here, is present you a presentation about stator vibration monitoring on turbo generators. It's not a secret that large turbo generators have issues with vibration. It's been an important part of our activities. So we'll look at some of the things that are present on turbo generators and what we can do to detect it, to measure it, assess it, and help customers ensure the long working condition of their units. Then we'll look at a case study on the hydro side, but instead of using a PowerPoint presentation, I will use the actual software that VibroSystM provides to show you a very clear case of being able to make decisions based on actual data instead of just guessing and wondering what the problem is. And then I'll introduce very briefly the platform that we've been providing for the past few years, which is our attempt to go even further in assisting the customers at various levels to have a better understanding of what their units are doing and how to manage these assets correctly. So if you allow me, I'd like to start the presentation, which is called Stator Vibration Monitoring and Analysis. So the presentation I have for you is, again, to monitor and analyze stator vibration, not just stator bar end winding, but stator vibration as a whole. So first and foremost, what are the actual driving forces behind the vibration that occurs on stator bars, winding cores, frames? Most people believe it's basically just driven by armature current. And obviously, it is mostly driven by armature current, but it's not only driven by armature current. The end winding vibration activity is actually usually much more complex, and of course for an analyst like myself, much more interesting. But again, it is true that the vibration signal can be as simple as a true 100 or 120 hertz, depending where you live, as the primary energy source, which of course is the armature current, and of course the electromagnetic forces. These forces create end winding basket oscillation amongst other vibration phenomena. If it's severe enough, this can easily compromise the structural integrity of the consolidated basket. So the basket is a structure that is designed to be both very, very stiff, but also very, very flexible. And that's why there are so many cases where serious issues occur, because it's very difficult to make something that is stiff, but is also flexible. So it's very difficult to do, and in many cases, problems occur. So when signs of looseness or excessive tightness, and we cover that in our training courses, according to temperature levels or after extended periods of operation, can present themselves, and these need to be dealt with if they're severe enough. So all of these different phenomena will produce very high 100 or 120 hertz vibration levels. The end winding basket oscillation that is produced in some cases can exert significant mechanical stress on the stator bars inside the slot. So if you have a high end winding basket oscillation, people will look at the end windings, will look at the end caps and figure there's some stress to the basket, which is true. However, that excessive oscillation can cause serious issues at the stator bar level in the slot. So if you have high end winding basket oscillation, in addition to stator bars which are not held in place adequately by the wedges, you can have serious stator bar vibration and eventually serious damage. So the stator bar failures are quite common in this area. Let's say the first 60 centimeters. It's pretty rare to see stator bar in slot failure near the middle of unit. It's usually at the ends where we have, among other things, this phenomena where the oscillation of the end winding basket will cause a tremendous amount of stress on the stator bars. So if we look at stator bar and end winding phenomena per se, there's four different variations that we frequently see. First and foremost, excuse me, the pure end winding basket oscillation I was talking about, where you can have high levels of vibration caused by the current and the flux. You also have rotor or shaft vibration that can contribute to a certain extent to end winding vibration, and during the training courses that we give, I show multiple examples of this. And I also have the issue of resonances. This is a common issue. Most people don't deal with those because these are dealt with by the OEMs or the consultants. But it's very important to make sure that you do not have any resonances that are anywhere near the line frequency. And last is the inadequate bar tightness that we see quite often, where the stator bar in slot is not well fastened and unfortunately is allowed to move accordingly and wear out. So if we look at pure end winding basket oscillation, we have a picture here where you can see how the arrow here points to the oscillation, which is primarily radial. You do have some tangential Also, you may have some axial vibration, but it's primarily radial. And you will have an end winding basket that will move back and forth, usually at 100 or 120 hertz. Okay. So for these purposes, there's a series of sensors that can be used to assess how severe this vibration is. So these are fiber optic sensors, different varieties. Some are single axis, some are dual axis, depending what you're trying to do. In some cases, people want to see how much radial movement there is, in addition to how much tangential movement, because the basket will not only vibrate, but also will have a tendency to torque. And to some extent, that can be severe and needs to be dealt with as well. The second point I was discussing is the rotor shaft vibration contribution. If you have a vibration from the shaft that is excessive, that vibration, that energy will be transferred through the bearings to the foundation, to the frame, core, and it will show up on the end winding themselves. And it will show up as a 50 or 60 hertz, which is the mechanical vibration fundamental, or for four-pole machines in nuclear power stations, you'll see a 25 and 30 hertz. And sometimes it can be quite high. It is surprising. You have an example here where at the top you can see the raw signal in the time domain. But if you do a spectral graph, a spectral analysis of this vibration, you'll see that we see the electromagnetic fundamental, which is the armature current, and the flux creating a 100 or 120 hertz. But you can see that this power station, they also had a high mechanical vibration. This vibration is coming from the rotor and the shaft. Okay? So in some cases, it can be excessive and it needs to be dealt with accordingly. Then we have the third point, which is component resonances, which contribute tremendous or can contribute tremendously to the overall vibration that you see. As I mentioned before, usually we don't really deal with this problem because the OEMs do so. The OEMs know that they cannot put a component on the unit that has a resonant frequency, or what many people call the natural frequency, that's anywhere near the line frequency. And when I say line frequency, I'm talking about 100 or 120 hertz, number of poles per second. If you have a stator bar that has a resonant frequency that is anywhere near 100 hertz, and the unit operates at 100 hertz, the bars will not last very long. They will fail very, very quickly. Okay, so everybody's seen in the past the example of a wine glass next to a speaker. You can put the sound as loud as you want. It has no impact on the glass. But if you generate a frequency that is at the resonant frequency of the glass, you do not need to raise the volume very much to see the glass break. Okay? You cannot excite a component at the frequency at which it dissipates energy, because it won't be able to dissipate and it will fail very quickly. So this is a common problem that is usually dealt with by the OEMs, but we see that quite often where units will have a natural frequency that will be away from the line frequency, but as they operate the unit, it is commonly known that the resonant frequency goes down as you increase the heat, because the heat will expand the copper, the epoxy, all the components, and that expansion will lower the natural frequency. And in some cases, you will see the vibration increase tremendously as the unit heats up. So these issues have to be dealt with. And one way to know if there is an issue is to have the monitoring system to be able to monitor this. This is just an example of a power station in Africa where I was called to do some testing because they had phase drops that failed twice in 6 months. And while I was there, they had this unit that had a well-documented resonance issue at the housing of the unit. And while I was there, the OEM installed these dampers on the frame, two on both sides. And what it does is as you loosen up the springs, it actually absorbs that vibration and it tunes down the resonant frequency so that the housing vibration was decreased tremendously. And the last one is the inadequate bar tightness, where again, if you have high end winding basket oscillation, if your bars here are not well fastened, they will actually be solicited and they will be bent, where you can see this area would act as a cantilever, and the movement here will cause the bars here to move, and a tremendous amount of stress is put on the bar in this location, and that's usually where the bars fail. If you have this issue, they won't fail down here, they will actually fail somewhere near the end core. If you look at stator bar and end winding schemes, typically stator bar vibration increases as the flux or the current increases, and the levels decrease as the core heats up and the bars expand. End winding vibration also increases as the flux or the current increases. However, in many cases, vibration levels increase as the windings heat up. So again, if you heat up the unit, sometimes you'll see the vibration increase, sometimes you'll see the vibration decrease. And it's important to know this so that you can understand the situation. So knowing that the end winding vibration has increased can mislead personnel to believe that the stator bar vibration has also increased. It may or may not be the case. So it's important. Vibration levels that may be acceptable in the end windings might be totally unacceptable for in-slot vibration. For example, if you have 50 microns peak to peak, that's quite acceptable for end winding vibration, also acceptable for stator bar vibration. But if you get 125 microns peak to peak for the end winding, that's still quite acceptable, but it's very high for stator bar vibration. So you need to monitor the stator bar vibration to be able to properly assess the situation. So we have a picture here of one type of sensor that is used. This one is actually inside that support plate looking at the stator bar. So it's looking at the stator bar movement. It's doing it capacitively, so there's no contact, and it records how much the bar is vibrating in reference to the core. Okay. This is another example. You can see the sensor is here. This is a spacer that puts it close enough so that we can actually monitor how much the bar is vibrating. You can see a 120 hertz signal. This is another type for those who do not want to remove wedges. You can install it on the top and looking at the bar immediately as it exits the core. There's also one that is used that looks through the wedge, where you drill and tap a hole in the wedge, and the sensor is then screwed in place close enough to monitor the amount of vibration of the bar. The ZPU 5000, these are the acquisition units we use to record all the information, and the software retrieves this information for analysis. We have here examples of fiber optic accelerometers, and you can see where the capacitive probe, which is drilled and tapped, installed in the wedge. And this is a case in Europe where the fiber optic accelerometers were used to confirm the vibration that was recorded by the capacitive probes. The OEM did not believe the amount of vibration, and fiber optic accelerometers were installed afterwards, and they confirmed the exact same amount of vibration. So now, end winding failure locations. The oscillation causes high levels of stress as the winding exits the core, which is why many failures occur at or near this location. Failures don't usually occur here. They will usually occur in this area here. Okay. Yes, the vibration is excessive here, which is mostly where we monitor, and the vibration will usually be lower here, but the failures, because of this torque that is bending the bars, the failures will occur here. We have here a very famous failure in the United States, where you can see the actual copper melted. In fact, it didn't melt, it evaporated. They found copper all over the place, and curiously or amazingly, this unit was actually repaired, and the unit has been totally replaced since then. As I mentioned before, in-slot failure locations are usually in this area. It's rare to see failures deep inside the unit. They usually occur within 60 centimeters of the end core. And some examples here, you can see cracks. So you can see evidence of vibration as represented by grease, by dust, and all kinds of signs of vibration. We have here an example of a raw end-winding vibration signal. This is real data taken in the United States, and you can see the vibrations were tremendously high. Everyone agrees that you should never be above 500 microns peak to peak, and this unit was at 860 microns, and this was a brand new unit. So this unit was in difficulty from the outset. You can see the same signal if you put through the fast Fourier transform. The primary source of energy was 120 hertz, very high levels. There was also a mechanical component, which is basically the vibration coming off the shaft. This is the waveform that we record when we look at stator bar vibration. So this was end-winding vibration, very high levels. This is a stator bar vibration. It's complex, but you can see that the levels are much lower. You have the 120 hertz stator bar vibration, but you can see the values are fairly low. Okay. Now, in some cases, it's necessary to monitor the stator core and frame. We see the core and the frame as these huge, massive pieces of steel or metal, and we assume that these are very fixed, very stable, very rigid, and they are rigid, but in some cases, they have issues, and it becomes necessary to monitor the vibration of the core and the frame to correlate with the end winding and stator bar vibration. In those cases, since you're usually far from the flux, piezoelectric accelerometers are usually used, but again, depending on the location. Some locations require the use of fiber optic accelerometers. Okay, so you have an example here of some piezoelectric accelerometers, and it's installed on the rib here, and they are monitoring the radial and tangential vibration. And one of the main issues that we look for when we're looking at the stator core and frame is we want to see whether the core and the frame are working together. Okay, the core is there to let the flux flow freely. It is there also to dissipate heat. It is there to hold the bars in place. But the frame is there to make sure that the core is able to be subjected to tremendous amount of torque when you convert the mechanical energy into electromagnetic energy. The core is seriously solicited, and the frame has to be able to absorb the energy to help the core function. In most cases, the core and the frame work together, but in some cases, there's looseness involved, and you'll see the core will oscillate and the frame will have sort of a delay where you detect some looseness. And we use these types of accelerometers to be able to detect that. And we want to see that before you start having grounding issue, you start having arcing between the core and the frame, and try to avoid some serious damage. There's quite a few cases where units have had core damage because of arcing, and in some cases the core, unfortunately, was not possible to fix it. It actually had to be replaced. I have seen in the past cores that have actually melted, so melted cores cannot be fixed. You have another example here where it's also looking at the rib and also looking at the back of the core. So we try to reproduce a dynamic representation of how the core and the frame are behaving to see if they're working together or there's some looseness involved. And you have another picture here of a piezoelectric accelerometer on the core. We have some data here from the core, so you can see we can detect how much vibration there is at the core level as well. And you can see if you do the fast Fourier transform, you will see the primary electromagnetic frequency show up as well. The interesting part is in this graph, if you have all of these different signals coming from different locations. For example, on the left we have signals coming from the core. In the middle we have signals coming from the stator bars, and in the end we have the end winding vibration coming from fiber optic accelerometers. And then you can look at all of these signals and see if they correspond to each other, if they correlate to each other. or if there are issues that need to be addressed. And you can see if you lose the same signals and you do a spectral analysis, you can see the end winding vibration, of course, will always be much higher because the end windings are much less supported than anything else. So they are allowed to move in the basket, so you will expect to see a much higher vibration at that level than anywhere else. But you can see that they all have the same frequency, which is the line frequency of the unit. So contrary to popular belief, stator bar position does move in the slots in response to increases in field of current. We did many years ago some tests. In fact, I believe those tests were in India. And they did a short circuit saturation test, and then they did an open circuit saturation test. And we were able to show that when you do a short circuit saturation test, you can see this is the actual position of the bar. And you can see when they did the test, the bar moved dramatically towards the air gap at a level of 110 microns, which is a lot for a stator bar. And when the test was finished, you can see how the bar slowly went back to its original position. And when they did the open circuit saturation test, it had some effect, but very little. So contrary to popular belief, the bars do move. They do creep in the slot. And it's important to monitor this to make sure it doesn't cause issues. Okay, so we could see the shift in the position was about 110 microns. And then the bar returned to its original position, and when they did the second test, there was some movement, but much less than the first test. So, to monitor vibration of core, bars, and windings, it has always presented certain challenges. The access is difficult, the environment is very difficult. Fortunately, there is monitoring equipment that exists today that can provide the critical data necessary to better understand the various dynamics involved. The advent of capacitive stator bar vibration sensor constitutes one of the more useful tools to help power plant personnel protect their machines. And that's the end of that presentation. The second case I wanted to show you is for the hydro field. And it's a case, of course, in my 25 years, I've cataloged many cases of issues, and we cover those in our training courses. And this is one of the cases that I show during the training courses. It's a power station in Canada, and it was a brand new power station, and it was actually for a paper company. And they have their own generation capacity to cut costs. They don't make enough for their own needs, but whatever they make, they are able to use in a cost-effective manner. And they decided to build this power station, one unit only, 18 megawatts, and it's a fairly fast unit for hydro, 360 RPM. And they decided to install some air gap probes for rotor stator dynamics, and they also installed 6 shaft relative displacement probes to look at the vibration of the shaft, and they also had some other equipment to complement their system. This was a customer who had our system installed on other units, and they were satisfied, so they decided to equip this power station as well. We have a picture of the sensor. This is not at the plant per se, it's just the type of sensor that was installed. They also installed some capacitive proximity probes for the shaft. You see different locations here. Okay. Now, when the unit started, the engineer on site, a gentleman that I knew, felt that the vibration was excessive. And after a while, he asked us to take some data and analyze and tell him whether his worries were unwarranted or whether he did have an issue. And one of the things he told me was that he had done a SOX test. And I mentioned, what's a SOX test? And he said, well, basically you just stand over the unit and you raise your pant leg and then you calculate how much time it takes for your socks to go down to your ankles. So it was his own primitive vibration test. But no, in reality, he said if you're on the unit, once they excite the unit, you can feel it in your legs. You can feel the vibration. And the OEM is telling us that it's not vibration. The vibration picked up by the sensors is actually electrical noise. So I said, well, send us the information and we'll take a look. So since he mentioned that the vibration seemed to occur when they applied the field, first thing I did was to go look at the upper guide bearing. Okay, this is the Zoom software, by the way, software we provide. And I looked at the field flash test. The unit ran up in speed and they applied the field. And this was the response. So I'm wondering if anybody can detect exactly when they apply the field. My guess, it would be somewhere here, right? You can see this is the process of the shaft. So the shaft is moving. And when they come here, the peak vibration increases tremendously. And then it settles down just a little bit. So you can tell that the vibration occurred here, the increase, which corresponds to the actual moment that they applied the field. Then I say, let's look at the lower guide bearing, 2 probes just below the rotor. Same thing. And they had 2 sensors at the turbine. Very little vibration. So you can see immediately for me, that means this is an electromagnetic problem. This is not a mechanical problem. Mechanical problems don't show up once you energize a rotor. You introduce issues based on the electromagnetic problem. However, the actual source of the problem may be mechanical, but this is a problem that is present when the electromagnetic forces are present. Therefore, there's an uneven electromagnetic distribution of the forces, and it causes this issue. The question is, why? Well, if you look at the upper guide bearing again, and if we look at the rotor using air gap sensors, wow, similar reactions. This is the shaft displacement, and this is the air gap. If I look only at the air gap, if you have some knowledge of air gap monitoring, if we look at only, let's say, one sensor, okay, this is the actual shape of the rotor. Okay, the rotor is spinning, and the air gap sensor is looking at the rotor spinning, and it's recording the profile of the rotor. And up until this point here, the profile of the rotor is fine. But when they excite the unit, the rotor seems to increase in size tremendously. Well, obviously, if that was the case, it would cause serious vibration, because if the rotor increases in size and in fact increases in distortion, it means that you will create a rotor that is not round. And if that rotor is producing electromagnetic forces, it's producing an uneven distribution of magnetic forces, which will obviously cause a tremendous amount of vibration. But the problem is, if the vibration is excessive, if you're an air gap sensor and the rotor is spinning but it's also moving, the air gap sensor doesn't know this. It doesn't know that the rotor is actually moving. It assumes that this variation in air gap is the shape. So how can you tell whether the rotor is out of round or the vibration is causing the issue? Well, let's look at the orbit pattern of this. The orbit pattern is the actual displacement of the center of the shaft. So we use 2 probes to calculate a hypothetical center, and then we see how this center moves while the unit is rotating. So we use the 2 probes, and at each pole we calculate a center point, and we see how that center moves. And theoretically, it should be quite stable within specified limits. Well, let's look at the orbit of this. And we can see it's quite high. Let me just reproduce the entire measurement. Okay. And I think you'll be able to tell when they apply the field. let me start that again. Okay, we can see the unit. I'm putting it very small because it will get very large very quickly. Okay, so the unit is spinning, and then when they apply the field, okay, so we can see that initially the shaft movement is more than acceptable. It's like 100 microns, which is more than acceptable. But when they apply the field, the path of the orbit becomes enormous, becomes tremendous, which is, of course, totally unacceptable. The bearing won't last if you do that for very long periods of time. So if I take, let's say, turn 136, and I put just one turn up on the screen. Okay, so if you look only at this orbit, okay, this is the process of the shaft. You can see these are all center points of the shaft, and this is one complete rotation. So the shaft did one complete rotation, and while it was doing so, we were able to record and trace the movement of the center of the shaft. Now, if you look at this result, although the results are extremely high, which is a very big problem, the orbit is stable. It is cyclic. It is a nice round profile. Now, if this result was before you apply the field, this would basically be a balancing issue. This would be just to find where the heavy spot is, put a weight, and compensate for this, because the offset, the imbalance is always in the same location. And our software has a specific feature where we can actually tell where the offset is. This is pole 15, pole 16. If I click anywhere, it's always between pole 15 and 16. Okay? So if someone wanted to balance this unit, what he would do is he would go opposite, and depending on the the apparent heavy spot angle, you adjust a certain distance and you put a weight, you put a counterweight. And that will reduce the vibration. And you can do that until you reduce the vibration to an acceptable level. The problem is here, this is once the unit is applied, once the field is applied. You cannot balance this. You cannot balance a electromagnetic problem. And since the vibration occurs when you apply the field, if you were to put a weight, you would have to put, I don't know, maybe 100 kilograms, because the vibration here is extremely high. What do you think is going to happen when you remove the field? Because with no field, the unit is very stable. If you introduce a very high counterweight, when the unit has no field, the vibration will be tremendous, probably causing a rotor-stator rub. You cannot balance such an issue. So in this case, we could see that the heavy spot was between pole 15 and 16. Well, if we look at the two-dimensional representation of the air gap, okay, and let me just go to the same turn, 136, and you'll see immediately what the problem is. Okay, can you see what the problem? This is the representation of the rotor at rotation 136, the same one as this one here. And you can see there's an imbalance between pole 15 and 16. Well, if you look at the cursor, if I go here, which is the center of this bump, it is at pole 16. So the problem is that this unit has a significant bump. The rotor is not round, so that when they apply the field, the magnetic field distribution is very uneven. It's very strong here, and it's much less strong in this area. So what happens? Well, the rotor will start doing this. And this is what's causing the vibration. So for this unit, the solution, unfortunately, was to remove the poles, re-shrink the rim, hoping that it's a installation issue, not a manufacturing issue, because if it's a manufacturing issue, they will reassemble the rim in exactly the same shape, and it won't solve the problem. So the issue here is a bump, and you cannot balance this problem. It has to be dismantled and repositioned. Okay? So since this was a brand new unit, our recommendation was to ask the OEM to resolve this issue. So I use this case study during our training courses because I think it's a very nice, simple example of how the air gap, rotor dynamics, and the shaft vibration can work together to quickly identify a problem. Okay? So that was this case study. So I wanted to show you a bit what we can do in the turbo field. These are only very small examples. We can do a lot more than this, but these are small examples with the time I have. And this was my example I wanted to show you for the turbo industry. And finally, since I've been giving training courses for, 20 years now, we always found that providing our behavior reports, providing the training, providing assistance is always helpful, but there is always a problem where a lot of the personnel that gets trained, that are experts in this field, they move on to other positions, they move on to other companies, and we were trying to get people to get more involved in the system that they had. And the best way that we felt we could do this was to provide a platform where we can do all the crunching of data. My department does all the analysis, puts it on a website where the customer can go at any time and look at the health of their fleet. If you have multiple units, you can go into the website and see how well each individual unit is doing. And I encourage anyone to go to see the demo on the web. If you go to zoomwatch.com, that's ZOOMWATCH.com, there are some demos and you'll have a feel for what the platform looks like. And basically what I wanted to show you is if you go on the website, what we do is we take all the different components. For example, on a turbo generator, we will use a rotor, stator, and shaft and bearings, and using different parameters, different sensors, different standards, expertise, we establish an operability level. And for example, in this case, the rotor had an operability level which is very good at 92%. The stator operability was acceptable at 64%, and the shaft and bearings at 84%. If you want to know more details as to what was involved in getting those results, you will go and look at what we call the phenomena where we establish a severity. So for example, in this one, the stator, we are looking at the stator core and frame attachment system. We're looking at the stator bar wedging system. We're looking at the end winding support system. And we're also looking at stator bar deterioration. And all of these different phenomena have sensors attached to it. Vibration sensors, flux sensors, temperature sensors, all kinds of different parameters that are used, and the results are used to establish a severity. This phenomena is okay, or is it critical? And we attribute a certain level to it, and levels that you can trend. And you can see this is a real example. You can see here where there's a break in the action. Well, it means that after this report, customer decided to take action and try to fix this. So they went in and they tried to fix the problem, and when the unit went back online, they improved the result, but as you can see, it was slowly going back. So they have a temporary result to their problem, but not a permanent one. So basically, the platform allows you to have access to data, to results, instead of doing your own analysis. And you have access to my department if you want some explanations, you want presentations, you want more reports. All of this is available on site. It also comes with a 24/7 alarm support system. Any alarms on site can be sent to my department, where we will look at the criticality of the alarm and tell you whether it's an issue or whether you can safely run the unit. And all the reports are available online at any point. You can download the report and have an idea of if the rotor results are bad, the report will tell you why, and it will tell you what to look for, what maybe you should do at the next outage. And it helps you manage your assets in a, what we feel, more efficient, painless fashion to get access to all of this expertise. So that's all for the presentations, Ravishek.
Yeah. Thank you very much, Andre. We have one question on comment box as well, and I have some more questions on my phone through a text message. So the first message, first question is from Sumya Sarkar. Can support customer is having a BMS of a different make? Can it be possible to integrate Vibro's analysis diagnostic software with the existing BMS?
That's a very complicated question because the answer is yes and no. Let's break it down into different examples, or let's unpack it. If you have existing equipment, for example, you have existing sensors, shaft vibration probes, temperature probes, you have existing equipment, and you would like to integrate into our system, that is perfectly possible. In fact, it's done quite often. For example, if you have RTDs on the unit, well, you can just connect the RTDs, or you can actually connect our system to your SCADA system, and we can retrieve information from your system, and your system can also provide, we can also send information to your SCADA, and we can retrieve information from your SCADA. If you have existing software or acquisition units, well, acquisition units, that's a little more difficult because we can't assume that the acquisition unit that you have is compatible with ours. Chances are it is, but it's not a elegant solution. It gets complicated. It's better to connect existing systems or our system into our acquisition unit and to have the diagnostics. If you have existing software, if your software is able to export data and you want us to look at it, that is also possible. Again, depending on the platform, depending on the type of information that you have, we will take a look at it and we can provide support. Obviously, it's much easier for us to get access to our own data because the system has one database. You know, if you look at end winding vibration, if you look at temperature, partial discharge, shaft voltage, stray flux, all of this information is recorded, and it's much easier to look at when it's in one database and you can correlate everything together. When you start having information from 4 or 5 different systems, 4 or 5 different file formats, it's very difficult to correlate. Plus, you can't be sure that the timestamp is exactly the same everywhere, so it makes it much more complicated. But it is possible, but it's on a case-per-case basis.
Yeah, thank you, Andre. I have another question. How can we perform the balancing through our Zoom software data?
How to do the balancing with the Zoom system data?
Yeah.
Okay, as I showed you in the previous case, with our system, it's very easy to detect where the apparent heavy spot is. We can detect where the apparent heavy spot is. We can also determine whether the apparent heavy spot location is stable, okay? Unfortunately, in many cases, people see they have high vibration and they start balancing without even establishing whether they're at the point of balancing. For example, we had a case not too long ago where they were trying to balance, they were having all kinds of issues and couldn't figure out why they were having issues. And in reality, when we had looked at the air gap data, the problem was that the rotor rim was loose, which means that from one rotation to the other, the shape of the rotor differs. And that was causing complex vibrations in the sense that the phase was not always in the same location. Well, if you take readings and the vibrations are high, but the phase is never in the same location, you're not at the point of balancing yet. You can't balance a moving post. It has to be fixed. It has to be relatively stable, so that you can establish where you want to put the weight and compensate. The Zoom software can detect the apparent heavy spot very easily, and it can help you very quickly to determine where you should put the weight and counteract the imbalance.
Okay, thank you, Andre. There is another question. If after 5 years a relative vibration probes increase relative vibration in guide bearing and velocity vibration not too much, may I think it is because of higher gap in paid in bearing?
Okay, the relative shaft vibration has increased, but the acceleration has not. Is that the question?
Yeah, they said velocity. Yeah, through the accelerometer or through velocity meter.
Yeah, it's quite possible. It's common. It's common to see the gap move. You should see a slight increase in the velocity as well, but you will definitely you can definitely see an increase in shaft vibration that is not necessarily proportional to what you will see in the velocity. And basically, that's again, as you mentioned, it's just because the gap has gotten bigger and it needs to be tightened. There can be other indications that will produce similar prospects. But if I were to see a trend and I would see the shaft vibration go up and the velocity not so much, that would be my first guess. It would be to check the gap and try to decrease the gap in the bearing. You should also see an increase in oil temperature.
Okay, there is another question. Please explain coupling effect of vibration.
That's a very complex question. I don't think we have the time to go into that. There are many reasons for that to be true. First of all, in some cases, we see the vibration will differ from up, middle, and top just because of a misalignment. We see misalignments, what most people call a dog's leg effect.
Yeah.
It can cause different things. We have a case right now where a customer is telling us that when they go from active power to synchronous condenser, for some reason they have very high megavar swings for a short period of time, and they're wondering why that is, and they're worried that these swings are so large that it will cause some issues to the shaft in regards to torsional torque. And we're actually preparing something to help them measure this, to see when they go through that process, do they see an excessive shaft torque? And if it's the case, they need to find out why that is, because the shaft may crack and fail. They have other units that are the same in the same power plant that do not have this problem. So they're asking our help to assist them in finding out if the phenomena they're having is just a short-term concern, or is it a severe problem that need to deal with? So it's a very complex question that will take a lot more time to go into, but it's an interesting question, yes.
I think we are done. We have some more questions. We will try to reply those questions later on.
Okay.
Rest people can also send me your questions on my WhatsApp, on my email, and I'll try to André will try to address all the questions.
Sure.
And thank you very much, André. Thank you everyone for joining us. Thank you.
I just wanted to mention for those who would like to see more videos, they just need to go to our YouTube channel, and we have a whole bunch of videos there for them to see. We have some Q&A sessions. We have some teasers. There's actually also a conference session that we did for the mining industry, which is still very interesting. So they can subscribe to our channel. They can click on the bell to get notifications when new data comes in. And I think they'll find it interesting, both the turbo industry and also the hydro industry.